Hi guys, welcome back to another video of me teaching, and today I have the hat check problem for you guys. And we are going to use some knowledge about derangements to solve this problem. So why don't we just get into the video? Well, first I'm going to explain to you what is the hat check problem. So say there are maybe 100 people who check into a party, and surprisingly they all have a hat on them. And then there's this game where everyone takes their hat off and puts it in a box, and then the game person shuffles these boxes around, and the question is, what is the probability that no one gets their own hat? And if you don't want to hear me, you can go to the end of the video and see what happens. Spoiler, it's really unexpected. Okay, so there are technically two ways to solve this problem. The first way is to use a recurrence formula, and the second way is to use a general form. And we won't actually use the recurrence formula, I'll just prove it to you guys, but the main point of this video is the general form, which is actually really beautiful. So, let's see. Well, to prove the recurrence formula, I'm first going to say that a derangement is a set of elements, a permutation of a set of elements where each element doesn't stay in its original position. For example, let's find a derangement of ABC. Well, so A can't stay here, B can't stay here, C can't stay here. So, one case is CAB, and the other case is BCA. And these are actually the only two cases for a derangement of three elements. So, this being said, you should actually keep this in mind because it's going to be useful. So, let's see. I'm going to say our set has n elements. Say first one is A1, A2, all the way to AJ, AK, AN. Okay? So, I'm going to first try and derange AJ. So, AJ can't stay here. So how many other places can it go to? Well, since there are n total elements, then this can go to n minus 1 different places. Now, why don't we just assume that AJ goes to where AK is? But now we need to see, where does AK go? Well, the first case is that AK goes to AJ. And now we have successfully deranged two elements. So there are n minus 2 more elements for us to derange. So it will have to be D n minus 2. And then for case 2, AK doesn't go to AJ. And similarly, we have only deranged one. Now there are going to be n minus 1 more elements for us to derange. So it will have to be D n minus 1. So, since these are cases, we add them up, and for this one, we have to multiply. So, we know that D of n will be, and just a note, I will define D of n to be the number of derangements, equals to n minus 1 times D n minus 1 plus D n minus 2. And the reason we're not going to use this, because to know D100, we need to do D99 and D98, and then so on, so on, so on, so on. And that will mean a lot of work. So, that being said, now I'm going to prove the general form. And for the general form, we're going to use something, and it's in set theory, that's called IEP, or the Inclusion-exclusion principle. We're going to first calculate the altogether permutations, which is n factorial, right? Because there are n elements. And then we have to subtract the permutation of any element that stays in its original position from the altogether, which in our case is n factorial. And next, I'm going to define capital A of I, define a set, capital A of I to be the set of permutations where lowercase ai stays in its original position. So I'm just going to write ai, and then to the left will be dot 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 and then dot dot dot. Okay? So next I'm going to define, and we actually don't need define because it's pretty straightforward, the cardinality of ai to be the amount of permutations. Okay? So now, what do we actually need to subtract from n factorial though? Well, the union of ai, right? And this means this, and I'll explain this later, I goes from 1 to n of ai. And this means, think of this as a sigma, right? So I goes from 1 to n, a1 union a2 union all the way to an. But what is this actually? Well, now we're going to use the inclusion-exclusion principle. Oh, and don't forget this. This is equal to, well, is this equal to just a1 plus a2 plus all the way to an? Well, of course not, because there would be so many overlaps here. So we have to subtract. We'll subtract what? Well, the pairs. So that will be a1 intersect a2, because that's the overlap, and then plus I'm just gonna write a dot 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 because I don't have space, and then a n minus 1 intersect an. Now, is this it? Actually, no. Now we have to add something. Well, why? I'm going to give you a quick diagram. So the simplest case is that we have 3 elements. So we subtracted off the pairs. Great. Yeah, sure. But we actually subtracted this off. We basically deleted it. So we need to add this back. So what is this though? Well, it's the intersect of all 3. So now we need to add back the triples, right? So a1 intersect a2 intersect a3, and then add all the way to I'm just gonna write this because I think you guys know what I'm going to write. And then we have to subtract the ones with 4 elements and then subtract all the way. But once we get to like the kth element, how do we know the sign? Well, first notice that the first term is a positive. So this will be -1 to the k plus 1. And then in the inside, since it's the kth element, then inside the cardinality would be k elements. So it would be a1 intersect all the way intersect to ak. And then we have to add blah blah blah. And then we go to the last term. I hope I can fit it. -1 to the n plus 1 of, well, inside will be a1 intersect a2 all the way to an. I'm going to make up the intersection sum as I goes from 1 to n of ai, right? So this means if you use your problem solving knowledge, this will be a1 intersect a2 intersect all the way to an. And I only wrote that because I don't have any space. Well, let's see. Is there any way we can simplify this? Well, yes, we're going to simplify it by a lot. So, let's see. If a1, let's first look at this. If a1 stays in its original position, or in other words, it stays fixed, then how many more are there? Then how many more permutations? Then how many more elements do we have to arrange? Well, n minus 1. And how many permutations? n minus 1 factorial. But this is not it. We need to multiply by how many cases there are, which is n, right? But instead, I'm going to write it as Cn1. And then if you do the same thing, this will be Cn2 and then n minus 2 factorial. And then for this one, Cn3, n minus 3 factorial. And then for this one, Cnk, because we said that this is the kth element, times n minus k factorial. And then for this one will be Cnn, n minus n factorial is 0 factorial. Okay, so I'm going to rewrite this all. So this is equal to Cn1, n minus 1 factorial. And then there, minus Cn2, n minus 2 factorial. And then plus, dot, 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 plus negative 1 to the k plus 1 times Cnk, n minus k factorial. And then plus all the way to this Cnn times 0 factorial. Oh, wait, I forgot the sign. Negative 1 to the n plus 1, Cnn 0 factorial. Okay, it just fit. Now, I hope you can read this. My handwriting is a bit messy, but okay. So, I'm going to rub everything out now because I don't have any space. And then, here comes the beauty of this question. Okay, now you guys might have seen a change in lighting because I thought it was too dark, so I pulled up the blinds for you guys. Now, moving on. So, now what do we do? Well, remember when I said, sorry I rubbed it out, we have to subtract the total n factorial. We have to subtract this whole thing from the total, which is n factorial, right? So, we have to do n factorial minus this. And once we subtract this, all of the signs will be opposite. So this positive will become negative, this negative positive. So this term would just be negative 1 to the k without the plus 1. So it'll be n factorial minus Cn1, n minus 1 factorial, plus Cn2, n minus 2 factorial, and then minus dot 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 plus negative 1 to the k, and then Cnk, n minus k factorial. And then, oh, I might not have enough space. This will just be negative 1 to the n. And then this will be Cnn 0 factorial. Okay. Oof. So, now what do we do? Well, I'm going to actually factor out an n factorial from this. Okay? So it'll be 1 minus this over n factorial. And then I'll just not write that. Plus dot 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 plus this, which I'll explain later. Actually, I'm going to write this here and then write this over n factorial. Okay? So Cnk n factorial. Yep. And then plus dot 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 plus this. I'm just gonna do the same thing. Okay. Now, I'm going to just take out this, not including this, and this is where cancel starts. So, I'm going to first write this term right here, Cnk n minus k factorial over n factorial. This is equal to, first I'm going to open Cnk which is the formula is n factorial over k factorial times n minus k factorial times n minus k factorial over n factorial. Look, cancel, cancel, and yet again, cancel, cancel. So this term will just be 1 over k factorial, right? And just don't forget to add this. Now, if this is 1 over k factorial, the k is here, or here. I'm just going to say here. So this would be 1 over k factorial, which in this case is 1. So 1 over 1 factorial. And that being said, I'm going to write it again. It will be n factorial times, I'm going to write 1 as 1 over 0 factorial, minus, we said 1 over 1 factorial, plus 1 over 2 factorial, minus dot dot dot, plus negative 1 to the k times 1 over k factorial, and then plus dot dot dot, plus negative 1 to the n, 1 over n factorial. Okay, and now we're going to look at the Maclaurin expansion of e to the power of x. And this is actually equal to the sum as n goes from 0 to infinity of 1 over n factorial times x to the power of n. And surprisingly, if we plug in e to the negative 1 into this sum, it will actually be 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial. And then, I think you know, it is the same. So, this being said, just keep this in mind, we see that this actually converges to 1 over e. So this whole thing is just n factorial over e. But we're not done yet, because we still have to over this, and what's on the denominator? Well, the altogether, which is n factorial. So the probability that no one gets their hat is this over n factorial, which is 1 over e. Now, 1 over e is approximately, so I shouldn't write this, is approximately 37%. I told you it was unexpected. And just a little note that this thing actually approximates to 1 over e, okay? So if we had only 2 people, it wouldn't be really close to 1 over e. But if we had 1 trillion people, then it would be super close to 37%, which is just mind-blowing. So the answer is 37%. And this answer gets better when the amount of people increase. So, thank you guys so much for watching, and if you enjoyed this problem, please consider liking and subscribing. If you want to master something, teach it.